for me, I always like to look at what does this look like, you know, on a phase noise plot. What are my filters? One of the common things, you know, is and we're going to look at that. One of the common things is a 12k to 20. Everybody knows what a 12 kilohertz to 20 megahertz filter looks like. It's a brick wall on the spectrum. But nobody really, at least I didn't until I plotted it out, knows what this looks like for Gen 3 and Gen 4. Well, here's what it looks like. So the vertical axis is dBc per hertz, and the top is at 0. The intersection down here is at minus 160 dBc. This is at 1 kilohertz, 10 kilohertz, 100, all the way out to 1 megahertz, 10 megahertz, 100 megahertz out here. So these different colored bands, these different colored lines come from plotting all of the different various values of PLL jitter peaking and bandwidths that are part of the spec on that prior chart. So this is the plot for the PCI Express Gen 3 and Gen 4 common clock filters. There's actually 64 of them. So technically, when we're calculating our clock jitter compliance, we have to apply all 64 of these filters to the jitter of the clock, integrate what's left to see what, to make sure we're in spec, and the spec changes. The good news again is that Gen 3 and 4 use the same set of filters, so I can do the same calculation. I can do the calculation once, and all I have to do then is apply the appropriate jitter limit. Gen 3 is 1 picosecond RMS. Gen 4 is 500 femtoseconds RMS, but the calculations are the same. That's great. It makes things a lot simpler. So what can we glean from this as far as what PCI Express might be sensitive to? What I want to do is, first of all, draw this is 10 kilohertz, 100 kilohertz, 20 kilohertz, 12 kilohertz is right here. So 12 kilohertz brick wall, well, if I could draw a straight vertical line, that would be cool, wouldn't it? But this is close enough. A 12 kilohertz brick wall looks like this, 12 kilohertz to 20 megahertz, and here's 10, here's 20. Looks like this. So let's call that 12k to 20 meg. So a 12k to 20 meg brick wall filter compared to the PCI Express filter, you can see that there's no attenuation here in the lower frequencies. Actually, there's no attenuation anywhere except it just dropped right off 12k20. So what can we learn from looking at this? Well, we can see that the PCI Express filters roll off a lot of the low frequency noise. It's assumed to be common clock, so low frequency noise is assumed to be common everywhere and everything tracks it. One of the intentional low frequency noise sources added to PCI Express oftentimes is spread spectrum itself. Approximately a 31 kilohertz intentional modulation, and it's low frequency and it's common, so everything is expected to see it and track it, and it does. So what we can see here is that PCI Express, for the most part, is, let me use a slightly different color here, is really the most sensitive in this region above 1 megahertz. This is 1 megahertz here. So all in here, and actually PCI Express goes up to Nyquist. So if I find my 20, 30, 40, 50, 20, 30, 40, 50. So this is the area here where PCI Express clocks are the most sensitive to noise for PCI Express Gen 3 and 4. So when I'm looking at this, I know that I want to try to minimize my noise in that region. This threshold right here is about it's about minus 10 dBc, approximately minus 10 dBc. So that is the area that PCI Express is most sensitive to. And then also you got to remember that it does go out to Nyquist, which in the case of a 100 megahertz reference clock is 50 megahertz. So basically 1 meg to 50 meg, PCI Express is most sensitive to jitter in that region, and that's why it's important to minimize jitter in that region. That's it for today. I hope this added a little bit of your understanding of PCI Express and how it differs from 12K to 20, which is a commonly understood and commonly visualized filter. Hopefully this lets you see a little bigger picture with PCI Express. That's it. Thank you.